For over 15 years, the Boeing 737 and Airbus A320 have dominated the skies. These narrow-body aircraft are the workhorses of global aviation, but they have reached a limit. Their traditional tube and wing design, where the wing is cantilevered straight out from the fuselage, has been optimized to its maximum potential. To achieve a 30% reduction in fuel burn and reach net zero carbon emissions by 2050. We cannot simply make incremental improvements. We need a radical new wing design. That is exactly what NASA and Boeing are developing together. The X-66A with the Transonic Truss-Braced Wing, or TTBW. What is a truss-braced wing? So, what makes the TTBW different? In a conventional airliner, the wing is attached only at the root, where it meets the fuselage. This forces the wing to be short, thick, and relatively heavy to handle all the bending loads during flight. The TTBW design adds diagonal trusses, similar to bridge supports, that run from the fuselage down to the midspan of the wing. These trusses carry the structural loads, which allows the wing to be much longer, much thinner, much lighter. In fact, the X-66A's wingspan is about 52 meters, more than 50% longer than a 737's wings. And because the trusses provide support, the wing can be incredibly slender. High aspect ratio and its effect on induced drag. This brings us to the most important aerodynamic concept in this entire design: aspect ratio. Aspect ratio is simply the wingspan divided by the average wing wide chord. A low aspect ratio wing, like a fighter jet's delta wing, is short and wide. It creates strong wingtip vortices, which generate high induced drag. A high aspect ratio wing, like a glider's wing, is long and narrow. It creates much weaker vortices and significantly reduces induced drag. The relationship is direct. Induced drag is inversely proportional to aspect ratio. Let me give you the numbers. Aircraft: Boeing 737 conventional, aspect ratio 9.5, induced drag level high to baseline. Aircraft: Airbus A320 conventional, aspect ratio 9.5, induced drag level high. But the aircraft X-66A TTBW, aspect ratio 19.5, induced drag level very low, approximate 50% reduction. By doubling the aspect ratio, the X-66A cuts induced drag roughly in half. This is not a small improvement. This is a fundamental aerodynamic breakthrough for a narrow-body passenger jet. Fuel consumption. How much less compared to 737 and A320? Less induced drag means less thrust required to maintain cruise speed. Less thrust means less fuel burned. The fuel saving comes in layers. 1. The wing alone. The high aspect ratio TTBW configuration reduces total fuel burn by 10% compared to the most advanced 737 or A320 today, even before you change the engines. 2. Adding next generation engines. When paired with ultra-high bypass ratio engines or open rotor designs, the total fuel burn reduction reaches 25 to 30%. 3. Lightweight composite structures. The X-66A also uses advanced carbon fiber composites for the reducing weight and improving efficiency. To put this in practical terms, a Boeing 737-800 burns approximately 2,500 kg of fuel per hour on a typical 1,500 km flight, and X-66A with TTBW would burn roughly 1,550 to 1,875 kg per hour for the same mission. That is hundreds of thousands of dollars in fuel saving per aircraft a year, and a massive reduction in CO2 emissions. Safety. Engine out glide capability. No, you may be thinking a longer, thinner wing sound fragile. What if an engine fails? The answer is surprising. The very same high aspect ratio that saves fuel also makes the aircraft safer in an emergency. When an airliner loses all engine power, it becomes a glider. The key performance metric for a glider is the lift-to-drag ratio. A conventional 737 has an L/D of approximately 16 at best glide speed. The X-66A's TTBW, with its dramatically lower induced drag, achieves an L/D of approximately 22 to 25. What does this mean for a pilot? The glide distance is directly proportional to the L/D ratio, lift to drag ratio. From 35,000 feet or 10.5 kilometers, a 737 can glide about 150 to 170 kilometers to a suitable airport. From the same altitude, the X-66A can glide over 220 kilometers. roughly 30 to 40% further. That extra 50 to 70 kilometers of glide range could mean the difference between reaching a safe runway and landing in rough terrain. The TTBW gives pilots more time, more options, and a larger safety margin after an engine failure. In fact, the TTBW's aerodynamics are so efficient that the aircraft behaves like a high-performance glider with a passenger cabin attached. How does the wing fit at the airport? You may be wondering, if the wing is 52 meters wide, how does it fit into existing airport gates designed for 737s and A320s? The answer is smart engineering, folding wing tips. Just like the wings on the naval fighter jets that fold for carrier storage, the X-66A's outer wing panels fold upward on the ground. This reduces the on-ground wingspan to approximately 36 meters, identical to a Boeing 737-800. The folding mechanism automatically locks the wing tips in the extended position before takeoff and folds them after landing. This allows the TTBW to operate seamlessly from any airport that currently handles 737s or A320s. What is the X-66A, the actual test aircraft? The X-66A is not just a computer model. It is a real flying demonstrator. NASA and Boeing are building the X-66A by heavily modifying a production MD-90 airframe. They will strip it down, remove the old low aspect ratio wings, and attach the new Transonic Truss-Braced Wing design with its truss structure. The aircraft is scheduled to begin ground testing in 2027 and perform its first flight in 2028. The goal is to prove that the TTBW configuration is aerodynamically efficient at transonic speeds, Mach 0.8, which is normal jetliner cruise speed. Structurally sound for thousands of flight cycles. Operationally practical with folding wing tips. If successful, the TTBW will become the baseline for the next generation of narrow-body airliners entering service in the 2030s. Why Transonic Truss-Braced Wing is a game changer? Let me summarize the 3 key advantages of the Transonic Truss-Braced Wing. The feature: high aspect ratio 90.5. Benefits: reduced induced drag by approximately 50%. Another feature, lower induced drag. Cut fuel burn by 30% vs 737 or A320. Another feature, high lift to drag ratio or L/D extends engine out glide range by 30 to 40%, safer landings. Another feature, folding wing tips, fits existing airport gates, 36-meter folded span. Feature, truss support structure, allows thin, lightweight wing without bending failures. The future of narrow-body flights. The Boeing 737 first flew in 1967. The Airbus A320 first flew in 1987. Both are brilliant designs for their era, but their conventional cantilever wings have reached their aerodynamic limits. The Transonic Truss-Braced Wing breaks through those limits by doubling the aspect ratio, cutting induced drag, extending glide range, and reducing fuel burn by nearly 1/3. The X-66A represents the first truly new wing architecture for narrow-body jets in over half a century. If you want to see where commercial aviation is going, the combination of aerodynamic efficiency, operational safety, and environmental sustainability. Watch the X-66A. Its first flight in 2028 will mark the beginning of a new era. Thanks for watching. Subscribe for more updates on NASA, Boeing, and the future of flights.